the end of my lecture tomorrow. So let's look into the basics of neuromorphic computing. So the fundamentals of neuromorphic computing. So this is what's available from IBM site. In IBM's view, neuromorphic computing is an approach to computing that mimics the way human brain works. It involves designing hardware and software that simulate neural and synaptic structure. So it's involving neurons and the synapses of the brain to process information more efficiently, especially energy-wise. It's a specialized computing system, replicates the way biological neurons communicate through electrical impulses. It's called action potential or spikes, aiming for high levels of efficiency, scalability, and adaptability in computing systems. Neuromorphic computing offers a more sustainable alternative to traditional computing, such as von Neumann, particularly for powering advanced AI systems. So human brain is known to be highly efficient. It's a golden standard in terms of energy consumption. And typically people say that the power consumption in human brain is less than 20 watt. So it's a very low energy. So in terms of the history of neuromorphic computing, it started in 1930s, actually. In early 1930s, the Alan Turing, he came up with a proof that computers can do mathematical calculations as humans if in the form of algorithms. So using algorithms, machines can do mathematical calculations like human beings. Then about 20 years later, 1948, 1950 period, Canadian psychologist Donald Hebb is he made a breakthrough in neuroscience when he came up with a theory that correlates the synaptic plasticity and the learning through synapses. That's what the Donald Hebb came about. So then Alan Turing, he captured that cognitive modeling machine based on human neurons. So, so in the beginning, Alan Turing proposed, and then 1948, Donald Hebb came up with some relationship between the synapses and the neurons for learning. Especially learning is done in synaptic synapses. So this is what we are going to discuss. We will show that synapse is like a memristor. Memristor is like a synapse. So by tuning the weight in terms of the memristance or memductance, we can train that machine to do learning. Then back in 1958, U.S. Navy created a program. Hello? Okay. They have a project for perceptron, for image recognition. So that was for a while active, but at that time, they only had the limited knowledge on how brain works. So it really didn't achieve the goal. In the 1980s, though, this is a really modern neuromorphic engineering by Professor Carver Mead at Caltech. He introduced the term neuromorphic engineering. He created the analog circuit that mimicked the structure and the functions of biological neural systems. So I mentioned that in yesterday's lecture. So Mead's efforts were the groundwork for future neuromorphic research, which helped design systems that emulate the behavior of neurons and synapses. See? So in today's engineering, it's between neurons and the synapses. So interconnection of them to achieve the neuromorphic engineering. So the early neuromorphic systems were mainly experimental, focused on understanding of how the brain processes information rather than practical computing application. I guess nowadays is more practical computing applications and the pattern recognition and among all the different things. So let's look into the AI, right? Artificial intelligence. Within it, machine learning plays an important role. And you can divide the machine learning into supervised machine learning and unsupervised learning. So ideally, if you have unsupervised learning, the better. But in supervised learning, deep learning is a core component of it. And it can be applied for speech recognition, language translation, pattern recognition, and so on. So deep learning can have many, many layers, even 100 layers. So it means that there are 100 different columns of neurons, and then each neuron pair, there are many, many synaptic interconnects. So if you look into the human brain, and especially if you want to do reverse engineering of a human brain for AI applications, it's a tremendous task in terms of scale. Number of neurons in human brain is a 10 to the 11, few 10 to the 11. So it's few hundred billions of neurons. It's a lot. Synapses count is even higher. Hundreds of or even thousands of trillions, of synapses exist in human brain. Yet the surface area of a human brain is only 2,400 square meter. It's like almost a handkerchief size. You fold the handkerchief in your pocket. So if you unfold it, that surface area is like a human brain's surface area. So in terms of brain statistics, surface area of human brain is about 2,500 or 2,400 square centimeters. If you look into the organization of a human brain, they are tightly connected to vision, smell through nose, taste through tongue, and then sound through ear. It's all connected to thalamus here, which is then receive it and relay to different cortex, auditory cortex, visual cortex, and then this olfactory bulb or olfactory cortex related to smell and so on. And then cerebellum here is related to the balancing our body. And also this thalamus, they say, is one of the main role is pain detection. Yeah. So when you feel pain, it's due to this unit. It's very, very complex how they interconnected together and so on. And there are many the ongoing lectures. So for instance, it's MIT Open Courseware by Nancy Wisher, talks about the structure of a brain, all the neurons and the synapses. And in terms of a scale, this body is in the range of meters, right? 1.5 meters or 2 meters, even tall person. Brain is much smaller portion, right? Brain is here, whereas it is a human body. And then the neuron is 10 micrometer That's the size here, right? Yeah. So 10 to the minus 2, 10 to the minus 10 to the minus, yes, it's about 10 micrometer. And then this is a sort of a model for brain interconnects. They also talked about the different partitioning of the brain. So, this Brodmann, 1868, 1918, 19th century, early 20th century, he identified 52 distinct areas, like organs. So this is a numbering of different areas. But the question is it really distinct? Can you really say that they are, a distinct unit? So it's arguable whether they are really distinct or not. And then there's also University of Washington, Seattle lecture on neurons. So neurons processes do not fuse into continuous reticulum. Instead, neurons contact each other at distinct sites called synapses. So neurons are connected through synapses. So there is axon, and then through synaptic junction, is connected to next neuron and so on. So this lecture here talks about how signals propagate through synapse. And so here, number one, action potential is a spike, right? Neuronal signal arrives, and then depolarization opens this calcium channel. So it gets into here and enters a terminal trigger exocytosis. So this is exocytosis, all this circled area. And eventually it diffuses, and then neurotransmitters are released. So it chemically released, and then it move into the postsynaptic ionotropic and metabotropic receptors. So it's moving into here. And then downstream effects, then reception happens. So it moves, propagates, and moves to next connection through. So this is another neuron area, but this is connected to the axon from originating neuron signals and so on. So it's very complex, but whether we understand fully about neurons and the synapses is still not fully established. So I'm quoting some news release, breaking news. In March 2025, researchers at my home institute, UC Santa Cruz, they published a paper in iScience saying that brain cells are more plastic than previously thought. The study shows using in vitro models of a specific type of a brain cell, scientists show that neurons are capable of changing from one type to another. It makes it even more complex. So biology is very, very complex, actually. But nevertheless, the current state of the art in neuromorphic computing is not yet accepting this sort of new facts yet. So this neuromorphic computing is initiated by Professor Carver Mead, this gentleman here, in his 90s now. He provided a theoretical intuitive answer in 1990 that analog computing should be thousands of times more efficient than digital computation. So that's the beauty of analog computation, especially Memristor's role in matrix multiplication in analog fashion, for instance. So he published the papers on retina on a chip, is a famous book. He had a silicon neuron and the analog VLSI and the neural systems, and then introduction to VLSI systems. So those are the really classic textbook at that time. Now, Professor Carver Mead had undergraduate students in his lab. In fact, he said that he learned the biology from undergraduate intern. This is a lady who was, either freshman or sophomore with a biology major. So Professor Carbamide, now an emeritus professor, has been instrumental in the development of chip design and was one of the first employees of Intel, Bob Noyce and Gordon Moore, which later became Intel. He's also one of the founders of the field of neuromorphic computing. So Carbamide and his student, biology major student, Misha Maho-Wald, working in the lab at Caltech on retina work. So that's how he started his work in 1989. And he said he learned the biology from this student and made all these groundbreaking studies. Neuromorphic chips, there are many. University of Manchester Spinnaker is one of the early ones. Intel's Loy High is another one. IBM True North is another well-known one. Heidelberg University's brain scales, that's another analog, the chips. And the Stanford University has a neurogrid analog also. And the ETH Zurich Dynap is a mixed signal chip. So there are earlier work on these neuromorphic chips. Now, this is interesting chart published in 1998. It goes back more than 25 years. And that time, Hans Moravecki, he plotted this progress in all these microprocessors and the computers and so on. And then he was sort of projecting where would it lead to in the year 2020 or thereafter, and what level would that be. So back in 1965, according to that early trend, it may be approaching monkey level. But 1975, 1985, even 1995, if it keeps progressing, then maybe approaching human level, human power equivalent per $1,000 of a computer, for instance. And indeed, that is what was happening. Back in 2016, I was at KAIST in Korea Advanced Institute of Science and Technology. And at that time, actually, we witnessed the AlphaGo competing with Lee Sedol for the Go game. So Go game is placed on this board here. This is a 19 by 19 grid system. And you play with the black stones and the white stones. Actually, usually what white stone means that whoever holds the white stone is more expert than whoever holds the black stone. So they gave some, in the beginning, some advantage to block black stone so that the game can be more exciting. So when the AlphaGo proposed a match between Isidore, everybody was laughing at it. How come computer can compete with the world champion in Go game? So they predicted that Isidore will have no problem beating AlphaGo, and they proposed 5 games. The first game was won by the AlphaGo. Second game was also won by AlphaGo. Third game was also won by AlphaGo, and then fourth game was won by Isidore, but fifth game again by AlphaGo. So the AlphaGo beat Isidore 4-1. That shocked the whole nation and the world, actually. So that was a demonstration of a deep neural network, which had more than 100 layers. Then they complained that was not a fair game. We had a humongous computer and then many supporting scientists, yet they were competing with one single person. So this shows a more vivid picture. These are the world champion in March 2016, March 9th through March 15. And yeah, so this is a board for Go game, 19 by 19 grids. So there are 361 nodes. So you place this the stone, black stone or white stone. And usually the whoever hold the white stone, let the black stone place first. So that's why it's 1, 2, 3, 4, and then white stone 3. So it's a matter of building how many more, occupy more this the points here, junction points. So whoever occupies more junction point wins at the end. So in AlphaGo case, more than 1,200 CPUs, more than 170 GPUs, more than 100 plus scientists supporting. And consumption, energy consumption was almost a megawatt, more than 600 kilowatt. If you look at all this, yet Isidore, he had one brain, less than 20 watt with coffee. So that's then after they so the result they say was not a fair game, but was still shocking in terms of competition. So I myself was surprised at the time. Now, actually, this prediction was made by the World Economic Forum. This gentleman is Klaus Schwab. Yeah, he's an engineer. And he's the one who started the World Economic Forum. It's held in Davos. So when I was at KAIST, I invited him. I also attended the Davos Games, the conference many times every year. And I invited him to come to KAIST to receive honorary doctoral degree. So this is a ceremony. The ceremony for conferment of an honorary doctoral degree on Dr. Klaus Schwab. He has many doctoral degrees, honorary degrees, but he accepted my invitation and came. But while he was coming to receive the honorary degree on September 7, 2015, he thought about what address he should give. So, he did a diligent preparation and came up with this book. He brought this book and gave a copy to me, The Fourth Industrial Revolution. So in it, he talked about first revolution, mechanical loom for textile, right? And then second revolution was the electrical energy with the electricity. Third industrial revolution was the computing systems. And then fourth industrial revolution, he said, will be really tremendous, will make a huge impact, cyber physical systems, including AI, in fact. So if you look at the level of sophistication, fourth industrial revolution, this level, second was here, third was here, fourth one way, way bigger. So in fact, his prediction was the first industrial revolution, progress, and then you have industrial revolution, second industrial revolution steeper, third industrial revolution steeper, fourth industrial revolution gigantic jump with very, very steep curve. So that's what is happening now. If you look at the Moore's law and the chip development, doubling every 24 months in terms of the complexity of chip, right? A number of transistors you can put into a single chip is doubling every 24 months. But in AI, GPT, GPT-3, 4, etc., is doubling every 2 months. You see that? It's a rapid progress. This is a challenge. So how do you catch up with this rapid progress and the demand for hardware support? That's a huge challenge in that regard. So this further illustration, right? So it's a gap is widening. GPT-4 is increasing like this while consuming megawatt nuclear power plant level of energy consumption. So how do you narrow this gap? That's what neuromorphic computing is all about. That's what the computing in memory is all about. How do you accelerate this hardware to catch up with all this thing? So that's the challenge here, right? Also, can AI, machine learning, outperform humans? So people in old days said probably not, but no, that's not the case. In fact, in Time magazine, May 5, 2025, revealed a very shocking story. While PhD level virologists scored an average of 22% in their declared areas of expertise, OpenAI's reached almost double, 44% accuracy. Google's Gemini scored 38%. It's far better than human beings. So this is a threat, not only for doctors, for everybody. In fact, this year in the US, many computer science graduates, they cannot get a job. Many of them. Why? Because entry-level job can be done by AI. So, company want to hire experienced the engineers, not entry level, because entry level job can be performed by AI. So that's a sort of an interesting challenge, isn't it? So that's where we are now. Now, why AI is doing so better? In fact, large language model, large AI models, is very interesting. These systems do not merely summarize information like library catalogs, internet search, and the Wikipedia. They also can reorganize, reconstruct the information. See, that's a generative AI type of a thing. They not only make information widely available, but also allows it to be reorganized, transformed, and reconstructed in distinctive ways. That's how they can outperform human beings even. But it's a database is huge, right? Cloud computing and also data center with lots of energy in it. So potentially create a more sophisticated means of solving complex problems, right? So in fact, it progresses so much that this year's Nobel Prize winning, this last year, 2024, Nobel Prize in Physics is won by Jeffrey Hinton. He's an AI scientist. Nobel Prize in Chemistry also by this Google people. Yeah, Google DeepMind. The Dennis Hassabis was the one who had a DeepMind competing with Isidore. So, but they solved some the unfolding of the helix, and for that contribution, they got a Nobel Prize in Chemistry. So, Nobel Prize in Physics, Nobel Prize in Chemistry done by AI experts. So that's the importance of AI and the impact. In terms of technology prediction and confidence level, so this is confidence level. C- is bad, A, B is good. The success in prediction, A+, and the C, D level. Remote learning and the computing is established one. High performance computing next established. In-memory computing next. And the machine learning still a lot to improve here. That's the threat, actually. If you advance machine learning and the in-memory computing further, that is going to really catapult AI even more. So that's the world that we are in now. That's your role for the future. Now, this is my chart. And I think there is the synergy between hardware and the software. I call S-curve. And, along this the vertical line here, left side is a hardware, right side is a software. They handshake. So what is happening is you have a software application, you have a new technology come to build the hardware, VLSI. So you build the VLSI, graphic processing unit or microprocessor chip, make it available, embedded in system, and then they develop software. In it, they can give feedback or run out of steam. They demand more hardware power, then it repeats itself. It develops next level of hardware, give it to software, they develop even more, and then they run out of gas and then demand even more. So this is like here. This is a S curve here. So one iteration here, next iteration, next iteration. So this is a S curve. So as you repeat this, that's how you make progress, increasing throughput as increase the integration level. So cascaded integration sort of increase this stepwise session like this, and this will continue with and for that you need a hardware acceleration. So you have to do hardware software co-design or use a new material system, new devices, and develop new hardware system. That's where Memristor will come in. So we saw this many times. So this is a silicon MOS transistor, and you can build a memristor even in the via hole here. So you can have this MOS transistor in series with a memristor, and this pair can be used in the crossbar array. So this is memristor, 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 and then sort of a switch to turn on and off to prevent what is called the sneak current. Now, there are synaptic connection here, but this particular case is what if it's a synapsis is a binary, either +1 or -1. And even that can do a lot. Very simple structure, right? Binary, +1, plus. So it can be +1, it can be -1, etc. So you have neurons and the synapses, and then produce output, either 1 or 0. And whereas in memristor case, it will be RRAM with a continuum of values, values. Yeah. So it can be, a two-state memristor, either high resistance, low resistance, or a continuum of the memristor values or memductance values. So we saw this one in a couple of lectures again, application of memristors to CMOS ICs, reconfigurable electronics, because you can program the memristors, right? So this is a voltage amplifier, adjustable, reconfigurable voltage amplifier. You can program the memristors or memductance through this pulsing signal, and then that itself can be applied to synaptic connector. So this is a neuron through synapse, and then they merge and then go through some register and then produce output. So here, see, neuronal signal comes in, it's weighted and it's summed, and then thresholding operation, and then output, right? So this is a biology versus neuromorphic computing now. So from biology and then hardware aspect of it. So if you look at the neuronal circuit, you have a neuron which outputs signals through axon, and then axon reaches synaptic connection point, and then moves to the next neuron, for instance. So this is the action potential. Yeah, the neuronal pulse signal, which can be approximated by like a pulse like here, digitally speaking, right? And so this can be with many inputs coming in with different weights and summed, and then go through thresholding operation, whether it exceeds a comparator circuit, it exceeds a certain value or not. If it's exceeding certain value, you have a firing here. If it's below that, it dies, for instance. So when you have this pulse operation in terms of a digital representation with some, there's a period up until here is 0, no signal. Now then 1, and the 0 all the way, for instance. So this is one coding of this signal, for instance. It has some timing information as well as magnitude information. So that's you can have the neurons connected through axon and synaptic link to another neuron. So that's how you can build this crossbar. You have V1, V2, V3 corresponding to V1, V2, V3, and then go through the synapse, and then summed up, and then go through a thresholding logic and so on. So neuromorphic computing in that regard, but biological process of neurons and their synapses are very complex, actually. That's very difficult to artificially simulate. Key feature of a biological brain is that all of the processing in neurons uses analog chemical signals. This makes it harder to replicate brains in computer because the current generation of computers is completely digital. However, the characteristics of these chemical signals can be abstracted into mathematical functions that closely capture the essence of the neuron's operations. So, axon is a long wire here, which involves some delay. But even current neuromorphic computing, we don't use this delay. But for different applications, you need to consider delay, for instance. And then there's a synapse point is here, for instance. So that, and then dendrite is even more complex. And people are looking into dendrite using so complex, using a three-dimensional memristive network. So dendrite pseudo 3D system have been implemented in multi-layer CMOS-based architecture, for instance. So in human brain mimicry, how do you do it? So neuromorphic modeling. So synapse is turned out to be mimicked by memristor. In older days, using SRAM to have some one value and zero value type of a thing, non-volatile memory type of a thing is a memristor, for instance. And the neuron, there's many different neuron model. We'll discuss that to that. So memristor crossbar array, that in that structure, this is a crossbar array. So you have to write contents into it. You have to read. So just like a memory, you have a read operation, write operation, and some control circuit and the monitoring the error, that sort of a thing. So biological neuron model, biologically inspired Hodgkin-Huxley model we discussed earlier of a spiking neuron was proposed in 1952. This model described how action potentials, spikes, are initiated and propagated. Communication between neurons, which requires the exchange of chemical neurotransmitters in the synaptic gap, is described in various modes. So there are integrate and fire model, Fitzhugh-Nagumo model, early 1960s, Hein-Marshi-Rose model, 1984, but most popularly used one is a leaky integrated and fire model called the LIF. It's commonly used as it is easier to compute than Hodgkin-Huxley model. It's a very, very complex, stiff nonlinear differential equation. So while the notion of artificial spiking neural network became very popular only during the first quarter of the 21st century, there are a number of studies between 1980 and 1995 that supported the concept. And the first model of this type of artificial neural network appeared to simulate non-algorithmic intelligent information processing systems. The notion of a spiking neural network as a mathematical model had already been worked in early 1970s. But the main point here is this is a leaky integrated fire model, and the spiking neural network is the main used using neuron model and the synapse model. So then the learning is happening in synapses, right? So plasticity via synapses. There are two kinds of learning, long-term learning and short-term learning. And this graph shows that, this is a memristor sort of, and whether your filament is fully connected, like here, or not connected, and then sort of weakly connected, almost connected. So when it is in unstable state here, it's a short-term learning, short-term plasticity. And when it's fully connected, a very solid one, it's a long-term plasticity. So this shows how you do that. If you apply pulse continually, narrow pulse, for instance, then charge accumulation and so on, the conductance change maybe accumulate and goes up, then fires back and then builds up and goes up again, and so on. So this is sort of related to short-term plasticity. It's a sort of a threshold value. So then you recognize, there is a connection. Whereas in long-term plasticity, where pulse width is longer, you see, pulse width is longer here. As you keep on applying it, it keeps on increasing and then establish itself. So this is a fully connected one. Conductance is high, right? And that's sort of a long-term plasticity. So it depends on the input pulse repetition time and the pulse width. And that determines you have a short-term plasticity or long-term plasticity. So this is about the spiking neural network. SNN is called, biologically spiking neural network. So, when you have a perception, say vision, you can detect some signal, and you can represent in terms of spiking all the signals, right? High density or low density comes in as an input. And then if you have a camera, and then you can sample and then create some spike input to represent the signals, for instance. And go through this spiking neural network, and then the output will be also spiking information. So that's the beauty of the spiking is there's lots of sparse, quiet area. That's sort of help us save energy in that regard. It's a sort of a sparse system, right? Spiking neural network. Spiking neural network is type of artificial neural network composed of spiking neurons and synapses. Spiking neurons store and process data similar to biological neurons, with each neuron having its charge, delay, and threshold values. And then neuromorphic architecture, synapses typically include a learning component, altering their weight values over time according to activity, right? So there's a potentiation and then depreciation type of a thing. Unlike a conventional neural network, SNNs factor timing into their operation. So SNNs are event-driven with the neurons and synaptic delay values, allowing asynchronous dissemination of information. So that's a highlight of spiking neural networks. And again, this is a spiking neural network. So if you have an image like this through vision, and if you have some grid system, this is an important object, right? So that's chi is here. So that is coded as 111, 1111, etc. The rest is 0, for instance. So you can code in terms of spike generation. No spike, and then spike 3 times, and spike 6 times, etc. So this is a membrane, right? Outer wall and the inner wall. So this is a membrane here. So in this case, membrane is penetrated by sodium molecules. So ionic channel sodium ion penetrate into this from outside to inner wall. That's when conduction happens. right? And then this is a leaky integrated fire model. So current comes in, and then it gets charged up. It's a leaky channel. And then this voltage is compared with the threshold. And when it's exceeded threshold, then spike comes out, for instance. So that's a leaky integrated fire neuron model. It's a simple one. So when you have a spike like this, signal, say, suppose the incoming current has a spike input like this, then it gets integrated like this, and then it dies down because of a leaky nature. But if they comes very closely like this, it piles up like this, and then reaches a threshold, fires, reset, and then next thing also piles up and fires, and then reset, and then piles up and fires. So in the output, you have 1, 2, 3. So this is the input stream, and after going leaky integrate neuron model, output is going to be spike 1 here and 3 here, for instance, right? So this is again another representation of a training spiking neural network using lessons from deep learning. So you have a this input and then output, and then you adjust the weight to make their correct. So you compare the training session, compare output with the expected output. If there is an error, then you change weight in the neural network until they are set. Then they function as a learned neural network and they can predict what's going to happen. So this is again crossbar array. We are neglecting the transistor as a switch, but that's how it works. Comes in, and when it induces current, add them up, and then go through integrated and fire model output. If it's not enough, there's no output signal coming in, for instance. And in this configuration, you have a D to A converter, A to D converter, but that's very costly. So the goal is not to use a D to A to D type of converters. Okay. So there is some algorithms, AI algorithms for spiking neural networks, hardware-friendly AI algorithms, take-home messages. Don't use floating point numbers. Makes very complex. Use spikes. Use binary weights even. It doesn't have to be. Don't use rate coding. So binary use is like a 0 and 1, right? Don't use rate coding. Use temporal coding because it has all the important information. Don't use a backward list of inputs to each neuron. Use a forward list of connections to output from each neuron. Use event-driven computing. Event-driven computing. To get best from a GPU, process a block of spikes, then check to see which neurons have reached the threshold. Learning can be done as a separate step. So there is a software called SNN Torch. My colleague at Santa Cruz, Jason Ashragian, he developed this SNH Torch software, gradient-based learning with spiking neural networks. So this is freely available from this site, snntouch.readerdocs.io, en latest index.htm. It has been downloaded more than 200,000 times. I think right now maybe about 500,000 downloads. It's very popular. It's a Python package for gradient-based optimization of spiking neural networks, real-time online learning, seamless integration with the PyTorch, CUDA plus IPU accelerated, lightweight enough for CPU. So it does handling of spikes coming in and then process it and produce output based on integrated and fire neuron model. So so if you want to experiment, this is a site where you can go freely download this software. So this shows some illustration. I'm sorry, let's see. So this shows how pulse coming in as an input, and then output comes out. This is enough excitation, and then beyond the threshold. So this is also what is happening in the output, leaky integrated and fire neural model. See, it repeats it intensely, then reaches threshold and fire, and then to that. Yeah, so I already mentioned many times, this is a ideal crossbar array, input signal coming in from neurons. And then this is a sort of a output column. And then, in analog signal, so people use ADC, analog digital conversion, but it's better not to use it. So depending on neuron model you use. So you have a neuron model here, outputting signal here, and then receiving neurons. So depending on what neuron model you use, you may not need A to D converter. This is an interconnect. There's a parasitic resistance in the wire. And then what's going to happen is, although you intend to just turn on this thing, the other memristor can be turned on accidentally. It's called the sneak current path. And in order to prevent that, you have a switch or a selector switch in series with the memristors. In digital computation, you have a matrix of conductances multiplied by input voltage to create the current. It's like a matrix multiplication, but with the analog fashion, when this is a memductance rather, then already current is flowing out. It's already done by Ohm's law. And then this Kirchhoff current law add them up together. So you don't need a addition operation. Multiplication is already happening according to Ohm's law. Tremendous savings. So I is equal to GB operation is happening in this crossbar array. Mag operation, analog computing. This is a big thing, actually. So this is a big thing. So that's where you have some appealing of the memristor crossbar array. This shows selector switch here. It can be MOS transistor or a different kind of a selector. And yes, so serial connection and so on. This is a sneak path that can be a noisy situation. So that's why you need a selector switch here. And there are many different kinds of a selector. Most mature one is an Avonic switch, OTS, Avonic threshold switch. And this is a MOS transistor in series with a memristor and the selector cell and so on. And this shows how memristorance or memductance changes. So as you apply this voltage, train of voltage pulses, and then if you monitor the current, in the beginning it's a full current, but you will see that it's gradually decreasing. So you can imagine the ideal memristor model where you have a voltage integration phi and the current integration Q. And then, suppose you have this type of a curve here, getting saturated. Then slope is in the beginning. So in this, this slope is the conductance. So you have a high conductance, so you have a high current. But as slope decreases, conductance decreases. Resistance rather increases, so you have a sort of a depreciation. Yeah. So this means that resistance is increasing, or conductance is decreasing in this fashion. That can be explained by this type of a model. And yeah, so this is memristor, and then the synapse in biological system. And how you can model this synaptic weight using memristor. The synaptic weight tuning, potentiation, and the depression So it's a linear and a symmetrical case. And then as you apply positive pulses like this, positive voltage is a potentiation. So that's, and then if you apply negative, then it's a depression. So the conductance can increase or decrease, depending on memristor. And then if you put a negative pulses, the opposite happens. So potential is increasing, depression is decreasing. And that is increasing of a conductance, and this is a decreasing of a conductance, for instance. And the memristor device based on the tungsten sulfide multi-layer with volatile switching. So this is 0 on, and then switch on. This is low resistance. So this is a high resistance. Then switch on to low resistance, and then stay there, and then come repeat itself. So this is the cycle, right? And this shows the two different values, low resistance and high resistance. Now, we revisit the Hutchinson-Huxley model, for which they got Nobel Prize in 1961, the A.L. Hutchinson and A.F. Huxley. And as we discussed earlier in the beginning, you have the inside of a membrane, outside of a membrane. And then in between is a membrane capacitance, and then across it is membrane potential. And then it has a sodium channel, potassium channel, and a leakage channel. And each can be biased to indicate the negative voltage, positive voltage, and so on. In the beginning, they said that this is a time varying the resistance, but in reality, as we discussed before, is a memristor here, another memristor. And this is how they experimentally verified this Hutchinson-Huxley model. It's called the giant squid. This is a giant squid, and they did the measurement of this membrane pulse here, action potential pulse. And eventually they came up with this mathematical equation, dVdt, C dVdt is current, right? And then 3 channels, potassium channel, sodium channel, and leakage channel. And then there's 3 variables, M, N, H. So they are probability functions varying from 0 to 1, right? So they all have the same form of equation here. So it end up this being a very stiff nonlinear differential equation, fourth order nonlinear differential equation. And yeah, again, this is action potential propagating through synapse. And it was the important paper by student Joe and his advisor Wei Lu at the University of Michigan. They published this one, nanoscale memristor device as a synapse in neuromorphic systems, NanoLetter 2010. And that's a well-cited paper here. So they explain that this memristor works as a synaptic device, mimicking this behavior. And that is an important contribution, actually. And this shows a thing, and then memristor representation. So you have a sodium channel, potassium channel represented by memristor. And then a leakage channel is a resistor, and then capacitor. And this is a giant squid from which they developed this model. The other learning is Pavlov learning, for which he got Nobel Prize in Physiology in 1904. So Ivan Pavlov, he discovers associate memory and the learning phenomena. And this is a classical conditioning problem using bell and dog. A learning theory known as classical conditioning has that behaviors can be learned through the association between different stimuli. Pavlov discovered this through his experiment with dogs, where he demonstrated that a neutral stimulus like a bell, see, bell doesn't have any smell, could elicit a conditioned response, salivation, when paired repeatedly with unconditioned stimulus, for instance, food. So dog will just salivate when it sees food because he knows it's tasty and he needs to eat, but wouldn't salivate when he just sees a bell. But when he's trained with the bell and the food together, after training, it's conditioned now. Even without the food, if he sees a bell, he will salivate, for instance. So that's a sort of a training issue. So here, before conditioning, if he sees the bell ringing, he doesn't salivate. If he sees meat, food, he will salivate. He wants to eat. If he sees, after conditioning, trained with a bell and the beef here, foods, he will salivate, keep on salivating, right? And then after that, you remove food, you look at just a bell, he will salivate because he's conditioned, he's brainwashed, he's trained. So somehow he's associating this bell with the food. So it's associative memory. And that is a Pavlov experiment. So this can be emulated, associative learning phenomena can be emulated by using memristor here. So this paper was published in 2015 by Lee et al. So he has some training, signals, a mid signal and the bell sound signal applied to memristor like here. And then he has a split R1 and R2, and then this is a output. And when you do that, simulate the bell signal, right? And then food signal response. So salivate when you see the food. When he sees only bell, will not salivate, right? And then when he sees the food and the bell together, it's a salivate. After training, he will salivate. And then lose it eventually. So memristor can be used for doing that sort of a thing. So that's sort of today's lecture here. And then I am open for your questions. We can have a more discussion today. So
Thank you very
see.
much. Thank you very much, sir, for your deep knowledge about your synapse and LIF and all the related things which will be used in neuromorphic circuits. So from the attendee side, if you have any question, you can ask.
See, I lost the contact on the chat box. Oh, the chat box is gone. Let me see whether I can get the chat box back. Chat. Let me see. Okay. So let's see. Is that today's question or no? No. 8:33. So this is the last one. What's
So
your
from
microphone?
Vaishnavi Rajesh, there is one question.
Okay.
How to calculate the non-linearity factor?
I'm sorry?
How to calculate the non-linearity factor? Linearity,
Non-linearity
non-linearity.
factor. Yeah.
Yes,
So
yes.
that's this a tricky thing. So you have to be very careful in programming the memductance or memdistance because you have to condition it. so that it doesn't drift away to the. So in order to have a stable operations, yeah, you have to signal properly so that otherwise it will drift to other region due to nonlinearity. So it's a signaling type of thing.
There is
And
one another question. Okay.
yes, question.
Yes, yes. Next question is, sir, people are doing analog switching in DC mode, then go for neuromorphic application. And his question is, it is possible that when we get digital switching in DC mode, and it can be applied in neuromorphic application.
So, okay, so can you explain that more? When you say digital switching, what do you mean, digital switching?
Digital switching using neuromorphic of application is, I think.
Good morning, sir. Am I audible?
Yes.
Yes, yes, yes.
Okay. So this is the question actually from me, sir. So digital
Yes.
switching means the sudden jump from the high resistance state to the low resistance state.
Right. Yes.
The sudden transition. So I am reading like people are reporting that whenever they get analog switching, like the slow transition, not the sudden gradual transition, they are then doing the neuromorphic applications. So, sir, is it possible in digital switching also?
So usually in neuromorphic application, it's a more analog fashion where you are either bottom curve or top curve, right? So in many cases, they are non-linear. So depending on
Okay.
where you stand on this nonlinear curve, you have different values of the memductance or memristance. So that's how you choose in the training where you want to, this operator that memristor. If it is a digital switching, it's a binary operation, right? So you can do either,
Yes, sir.
0 or 1 type of a thing. So yeah, it's a binary
Yes,
operation.
yes.
You can do that. Yes. But it consumes more
Okay.
energy.
Okay. Thank you so much.
You're welcome.
Professor
Any
Kang,
other question?
yes, Professor Kang, I have a question regarding the crossbar architecture that you've shown in a few slides back.
Yes.
You talked about the parasitic when there is no switch, either a transistor or a diode. So what is the scenario if there is a transistor or a diode that's used as a switch? And what is the contribution of the parasitics from the switch?
Yes. So yeah, so the switch itself will have the drain to source resistance, right? So in order to have a stable operation, reliable operation, your memristance value should be much higher than those parasitic resistances. Yeah. So you have to. The interconnect issue is always interconnect parasitic is always challenging. So you have to overcome that. And in that regard, if you use wire too narrow, then it will introduce lots of series resistance. So you have to be careful that resistance compared to memristance value, either low or high, is much smaller, right? And in many analysis, actually, the drain to source resistance is neglected in simple analysis, but they are there.
Thank you.
You're welcome. Any other question?
I think there is no question, sir. So we can conclude up to today.
Okay, thank you.
Thank you, sir. Thank you. Thank you, sir.
Thank you. Okay, bye-bye.
Bye-bye, sir. Good night.
Bye.
You want wait.